We want to find the surface area of the helicoid or spiral ramp with the vector equation shown here over the given region. Let's first take a look at this graphically. So here's the graph of the vectored valued function. Our goal here is to find the surface area of this helicoid or spiral ramp. So because the surface is given as a vectored valued function, we'll be using this formula here to find the surface area. So notice how we'll have to find the partial derivatives with respect to u and v, then find the cross product, then find the magnitude before we evaluate the double integral. So let's work on finding our partial derivatives. To find the partial of r with respect to u, we differentiate each component with respect to u, treating v as a constant. So the derivative of u cosine v with respect to u would just be cosine v. The derivative of u sine v with respect to u would be sine v. And the derivative of v with respect to u would be 0. And now for the partial of r with respect to v, we differentiate with respect to v, treating u as a constant. So the derivative of u cosine v with respect to v would be u times negative sine v, or negative u sine v. The derivative of u sine v with respect to v would be u times cosine v. And the derivative of v with respect to v would just be 1. And now I need to find the cross product of these two vectored valued functions. So the partial of r with respect to u crossed with the partial of r with respect to v is equal to the 3×3 determinant, where the first row would be I, j, k. The second row would be the components of the partial of r with respect to u. So we have cosine v, sine v, 0. Third row is going to be the partial of r with respect to v. So we have negative u sine v, u cosine v, and 1. Let's go ahead and evaluate this on the next slide. So using the expansion by minors method, for this first 2×2 determinant, we eliminate row 1 and column 1. So we'd have sine v, 0, u cosine v, and 1. For the second 2×2 determinant, we eliminate row 1 and column 2, which would give us cosine v, 0, negative u sine v, and 1. And for the last 2×2 determinant, we eliminate row 1 and column 3, so we have cosine v, sine v, negative u sine v, and u cosine v.
Therefore, the x component is sine v times 1 minus 0 times u cosine v, which is sine v.
For the y component, the determinant is equal to cosine v minus 0, that's cosine v, but because of the minus here, we have negative cosine v. And for the z component, we have u cosine squared v minus negative u sine squared v, which is u cosine squared v plus u sine squared v. Notice how here this is going to simplify. If we factored out u, we'd have u times the quantity cosine squared v plus sine squared v, and cosine squared v plus sine squared v is equal to 1, so the z component simplifies nicely to just u. So the partial of r with respect to u crossed with the partial of r with respect to v is equal to the vectored valued function with the x component of sine v, y component of negative cosine v, and the z component of just u. So going back to our first slide, now that we have the cross product, now we need to find the magnitude of this cross product. And let's do this on the next slide. So we'd have the square root of sine v squared plus negative cosine v squared plus u squared. And notice how this is going to simplify nicely. We'll have the square root of, this is sine squared v, plus here we'll have cosine squared v, plus u squared. Of course, this is equal to 1. So the magnitude of the cross product is equal to the square root of 1 plus u squared. So going back to our first slide again, we now have all the information we need in order to set up this double integral to find the surface area of the helicoid. The surface area, S, is equal to the double integral of, again, the magnitude of the cross product is equal to the square root of 1 plus u squared. Now for differential a, let's use du dv. Now for the limits of integration, for u we integrate from 0 to 1, and for v we integrate from 0 to pi. Now let's go ahead and evaluate this on the next slide. When we integrate with respect to u, though, it's very challenging to find this antiderivative, so we're going to use the integration formula shown here below from an integration table. But to make it better fit this formula, let's rewrite this as the quantity u squared plus 1 rather than 1 plus u squared. Looking at the integration formula below, notice how a squared is equal to 1, and therefore a just equals 1. So now we integrate with respect to u, so we're going to have 1/2, and then we'll have u times the square root of the quantity u squared plus 1 plus a squared, of course, is just 1, so we have natural log the absolute value of u plus the square root of the quantity u squared plus 1. So all of this is the antiderivative, and we're integrating with respect to u from 0 to 1. So now we have 1/2 times the integral from 0 to pi, and now again we're going to substitute 1 for u and then 0 for u. So when u is equal to 1, notice how here we're just going to have 1 times the square root of the quantity 1 squared plus 1, that's the square root of 2, and then plus natural log absolute value of 1 plus, this is going to be, again, the square root of 1 squared plus 1, or the square root of 2. So this is the value when u equals 1, minus when u is 0, notice how we're going to have 0 here. So we'll have 0 plus natural log. And again, if u is 0, we have 0 plus the square root of 1, which is just 1, so natural log 1. But notice how natural log 1 is equal to 0, so this simplifies out. Notice how all this is just a constant, so let's write this as 1/2 times the quantity square root 2 plus natural log absolute value of 1 plus square root 2. All of this times integral from 0 to pi of dv, or if we want 1 dv. And now we integrate with respect to v. Well, of course, the antiderivative of 1 with respect to v would just be v. So this gives us 1/2 times the quantity square root 2 plus natural log absolute value of 1 plus square root 2 times, well, of course, when v is pi, we have pi. When v is 0, we have 0. So the exact value of the surface area is equal to 1/2 pi times the quantity square root 2 plus natural log. We actually don't need the absolute value here because that's positive, so natural log of 1 plus square root 2. Let's also go to decimal approximation for this surface area. So the approximate value is 3.6059. And this is surface area, so the units would be square units. Here for the approximate value, as well as here for the exact surface area. Which is the surface area of this surface here. I hope you found this helpful.